Okay. So please go ahead, sir.
Yeah, Bakulji, please.
Okay, I'm Bakul Shah from Chennai. I run a die casting company in aluminum, representing BMW Auto Components. We are into die casting for the last 20 years.
Welcome,
Job.
sir. Nice to meet you. Yes, sir.
Job.
Sir, yeah, good morning all. My name is Job Yuvraj, and I was into ferrous for quite some time, for 16 years. Now, recently I've joined CX. It is called Chinching India Limited, which they do for 5G components. It's aluminum die casting. And we have variety of machines like from 1200, all LK machines, 1250, 1600, 2500, and 4500. And we are located in Sri City, and we have a plant which is there in Nellore. So we do around 200 to 500 crores roughly. So last year it will be around 240 crores of business.
Great.
Okay, thank you, Job. Uday
Thank you,
Kumar.
sir. Thank you, sir.
Yeah. Mr. Uday Kumar. Mr.
DMW
Arun
Uday
Kumar.
Kumar, sir.
Are you in the line?
Okay, sir. Tech mold, sir. The tech mold, Patel, sir, my MD. 650 machine, I'll take care, sir. Total as in charge.
Okay, okay. Mr. Arun Kumar,
Yes, sir.
introduction of yourself.
Yeah, sir. Die casting plant unit, sir. Tech mold.
Technology. So where are Bhavana? Who is Mr. Bhavana? Mr. Bhavana? Are you there? Okay. I am Anbu Chelvan,
Okay.
proprietor of Insat Corporation. We are into die casting in all three forms: pressure die casting, gravity casting, and sand casting with a full-fledged machine shop. We have our own product and the brand name of Flow. It's a bottom loading system for oil and gas segment, mainly for the oil tankers. And once again, thank you all for introducing yourself. Now it is almost 10:35. Shall we start the meeting, sir? Thirugnanam, sir?
Yes, sir. Please, sir. Please go
Yes,
ahead.
sir. Okay, gentlemen. Now we are in the meeting, national webinar for non-ferrous series. This is the second series we are having. It is conducted from Chennai. And Mr. M.Thirugnanam is a veteran in Aluminium Foundry. He will be properly introduced by our Mr. Bakul Shah. He is taking this session. I welcome first M.Thirugnanam sir, and thank you for offering yourself to take this session in spite of your health condition. Really, I am very, very happy to see you again active, taking part. Please be always with us. You are our guide, and you are our energy for us, for the non-ferrous. We always need you. I welcome Mr. Ashutosh Sharu, who is a coordinator, and he is the one person instrumental in carrying out this mission, because every one of us are quite busy in our own day-to-day affairs. He is the one behind this. I welcome Mr. Arun Kumar,
Yes, sir.
Mr.
Yeah. Okay, sir.
Job Yuvraj, Mr. Uday Kumar and Bhuvan. I can't see their faces. I welcome you, and whoever is going to join, I welcome you all. At this time, I would like to thank Mr. Prabal Sen, Chairman of Non-Ferrous Committee, who is a key person who wants to conduct this session without any break. He's after me always. I thank him. I thank him at this time. And our Sir Chairman, Mr. Palani Murugan, and Sir Secretary, Ramesh Babu, who are very much involved in these activities. I also thank them. And Mr. Prabhakaran, Chairman of Non-Ferrous Committee, Bakul Shah, and the Secretary for Non-Ferrous Committee. So I thank both of them being a part of our this mission of non-ferrous. We are all trying hard to take non-ferrous to the national level and create a strong vertical in parallel with the ferrous. With this, I welcome you all, and I hope this session will be really useful. The topic is really a wonderful topic. Yield improvement in aluminum castings. We all work for it only. Yield improvement means cash improvement. Cash improvement means profit improvement. Profit improvement means we are all going to become wealthy by hearing this session. I request Mr. Thirugnanam sir to make us wealthy, sir. Please. I request Mr. Bakul Shah to introduce Mr. Thirugnanam sir in appropriate way. Thank you, gentlemen, for giving me this opportunity.
Thank you, Anbu sir, for this opportunity to introduce Thirugnanam sir. As we all know, our senior sir, Thirugnanam sir, is specialized in aluminum high pressure die casting, gravity die casting, and tilt gravity die casting. He's got an experience of 35 years, consulting experience of 15 years, and a training experience of 20 years. Thirugnanam sir is a BE mechanical engineer having around 50 years experience from wide spectrum of aluminum foundry industry and foundry processes. Able to speak in Japanese, Chinese, German, and understands Korean, Spanish, and Italian. He's trained in Buhler, Switzerland, and in Suzuki Motors, Japan, in high pressure die casting and gravity die casting. Sir is also trained by Daerim Hyundai in South Korea and Bridge Foundry in England in gravity and tilt gravity die casting. Sir has presented technical papers in World Foundry Congresses held in China, Spain, Japan, and many Indian foundry congresses. Published technical papers in modern aluminum high pressure die casting in Google and Indian Foundry Journal, in many more magazines. He's also received the best award for year 2020 in Indian Congress held in Calcutta in September 2021. Sir has written many books, mainly Technology of Aluminum Gravity Die Casting through Case Study. The book was fully sponsored by Institute of Indian Foundrymen, Calcutta. Positions, Sir has held various positions, which include he is a unit manager of pressure die casting in Sundaram Fasteners. He's worked there for 35 years. General manager in Dynamatic Technologies, ancillary of Hyundai Motors in Sri Perumdur for 4 years. Retainer, he's retained as a TQC at Sundaram Clayton for training of workmen to get and engineers. Proprietor of Samurai Aluminium Foundry Consultancy. And sir is also a technical consultant to many foundries in Gujarat, Delhi, Bangalore, Coimbatore, and Hyderabad. And the domains of expertise. Sir is expertise in training of engineers and workmen. He's expertise in 7 QCs, 5S training, and in Tamil also in the foundries. His core area is new dies proving problem solving in the shop floor, and he's guiding design engineers for die design in PDC and GDC. Sir, this is too much to explain. Welcome, and we look forward to your presentation, sir. Over to Thirugnanam, sir. Thirugnanam, sir. Anbu, sir.
Yeah, Bakul sir, we can hear you. I think Silesh is just connecting.
Yes.
Yeah.
Job, did you speak to Shailesh?
Yes, sir. I'm just calling him, sir.
One thing that's not mentioned here in the introduction is one instance that I remember, like about a year ago, I was struggling with a complex alloy, and I discussed the subject with Thirugnanam sir, and he very easily just told me to add a couple of elements in the alloy, and my problems were solved. So sir is also good and has his expertise in metallurgy. So that's another area which can be very helpful to a lot of die casters here for special alloys.
Sir, in a couple of minutes, it get connected. It got freezed. Yeah, the screen got freezed.
Hello, am I audible?
Yes, sir. Yes, sir.
Yes, sir, you are.
Yes, sir. Please proceed.
Good morning.
Morning,
Good
sir.
morning, sir.
Good morning.
Sir.
Thank you for the nice words from Mr. Anbuselvan and also Mr. Bakul Shah.
Pleasure, sir. With pleasure.
Let us start the presentation. The topic chosen is yield improvement of aluminium castings. I would like to present it through case studies, which will be more useful. Aluminium castings are being produced in many ways. A few of them are below sand casting process, gravity, tilting gravity, high pressure, low pressure, and counter pressure, and fuse gas. And so many are do that. Unlike the other processes, in the foundry process alone, metal has got to be melted and made as liquid and poured into the dies or molds. It solidifies and becomes solid. Due to high volumetric shrinkage, about say 6.6% from liquid to solid, and also for many other reasons, more volume of molten metal has got to be poured than the net casting. This cannot be changed. As the ratio is called molten metal yield. Percentage yield is calculated by a formula: weight of the net casting by divided by the weight of the full shot into 100. So it expresses in percentage. Now let me see how the various processes are giving yield. In sand casting, the yield is very low, hardly 20 to 30%. We have to pour metal, much more metal. And gravity casting, 40 to 50 kg. Suppose if you want to make a casting of 1 kg, you have to pour about 2 kgs of metal. Tilting gravity casting, 55 to 60% yield. High pressure, 55 to 65%. Low pressure, 90 to 95. The best process. If you want to make a casting of 1 kilo, it is sufficient. You pour about 1 to 1.05 kg. Such a very good process. Counter pressure die casting also excellent. Used for thin walls and also big casting, 95 to 90%. Excellent yield, but it requires a lot of investments. Fuse casting also 80 to 85%. Used mainly for very thick castings where you don't want the blowholes or shrinkages. All are squeezed out. Floating piston casting is about 90 to 98%. Number one, this is being followed by for Hyundai Foundries. An excellent process, a variation of the low pressure die casting. So, of all the processes, the best one is low pressure die casting. Some general guidance for reducing the riser and rush. A casting has got two portions. One is the riser, one is the casting. Riser cannot be sold or riser is a waste, but it is required for the process. Casting portion only people will buy it. And there are some general rules so that the risers can be minimized. Pouring from the top of the cavity is the most economical way. The riser size will be minimum. Side gating also useful for very tall castings. Bottom gating is the most uneconomical way because of the bottom runner and the top risers. You have to pour cold metal only reaching the riser. Never go for bottom gating unless you are warranted to go for it. Make the riser cavity and casting cavity as a separate blocks in the dice. Supposing if you want to modify the riser, that riser cavity alone can be made separate. But the tendency of the die designers and die makers is to machine the die as a whole. That is, the riser cavity and the runner cavity and casting cavity also in one block. It will be very, very troublesome for any changes. As the Professor Dr. Campbell, the man from UK, has done a book on casting. He said, in aluminum casting, when the sections, no riser is required when the section thickness is 6 mm and below. Do not give more risers. More risers, more problems, more fettling, all that. The above may be bear in mind when you make a die design. Selection of the process for any casting. If the volume and the weight is justifiable, try to go for low pressure die casting where the yield is 90%. Feel it very economical. Although the initial investment is high and the die design is difficult and complex, yield will be very high. Settling also will be very easy. Or go for tilting gravity die casting for thinner castings, where the filling will be easier. The riser and the runner are one and the same. You can use the riser itself as the pouring, as a runner. The backside of the riser cavity should be made hollow, so that it will be thinner, get not very quickly. The die coat thickness on the riser cavity should be at least 3 to 4 mm for retaining the heat. The above will reduce the riser volume. In this presentation, I would like to present some of the real life case studies from the shop floor. These dies had been, what I'm going to show, had been already made and used for production, but with a very low yield. Lot of effort had been put to improve them. Some of the dies had been scrapped to make, and then we made a new die. I hope the case studies will be interesting to you. This is one casting, cylinder casting. It weighs about, this is a settled casting, 3.6 kilograms of weight. Casting information is a cylinder. Alloy is LM4, settled weight is 3.6 kg, short weight is 7.5 kilograms. The process is static gravity die casting. Die material is ENH steel and cast iron, but the quality level is very, very critical. The air pressure test is at 12 bar. Finish requirements also very high in the board. Very critical casting. See, the settled weight is 3.6, but short weight is 7.5 kg, which is very high. At present, it is only 48%. This is to be improved as per the management's instructions. This is a running die. There are all the various parts of this one. There are 3 risers, top risers. 1, 2, 3. There is, this is the side bulb riser to feed this part. This is the casting portion, and this is a side gating metal comes over here and depressed here and enter in this one. Once it's filled up to here, it also fills the top bases. This is the full shot of the casting. All these are causing are necessary to make a casting. But how to make better? How to reduce the metal? So the first thing is we wanted to eliminate these bulb rays. So whenever you do any changes to the casting, please have the machined sample along with you. We did that one and we found that if the material can be reduced in this to 36 bars, and we found in this one M24 tapping is done. So what a material can be removed. The material can be reduced, this feeder can be eliminated. Then the material, see, one of the fundamental approach for shrinkage is, number one, explore the possibility of reducing the wall thickness or the casting material if the design permits. This is the first step to be followed for solving any shrinkage problems. Luckily, we have this 36 dia being tapped to the M24. So a core was introduced in the die newly, a 16 dia core. So nearly so much length and the material has been removed in this one. And a batch of 100 has been produced, no shrinkage in the M-threaded holes, and successfully we have eliminated the bulb eraser. This is the view after removing the bulb eraser. It weighs about 100 grams. Second, removal of the side gating, providing a top gating with a control flow. This is a very difficult task. How are you going to remove a metal which is running through this one and coming through and all? You are touching the very critical portion of this one. Then how to fill the casting on this one? We try to go for a top eraser. If you can succeed by eliminating this one and provide the top gating, which is very economical. I said in the starting, always pour metal from the top. Always hot metal will be there in the rail. With a lot of discussions, plus and minuses, we decided to try this in the second die. Yeah, this is the shape. We have eliminated all the bulb erasers and try to go. This is the runner. The cross-sectional area for this one is 1:4:2 area cross-section. Metal comes over here, depressurizes it, and follow it. Its height will be nearly 150 mm, and metal falls on the top core, so it you and flows down. So hot metal is always there in the eraser. If we can achieve this one, or something like that, it will be very good. But it is not easy. This is the running system we proposed. These are risers. So the die was extensively modified and the yield went up to 58%. But I'm going to give the flashback how it was achieved. It's a mind-boggling story. It was not that simple and easy to achieve this improvement. Eliminating the side gating and go for a top gating is over. A series of mind-boggling stories will come. We shall go through one by one. The first problem in the top gating was faced by shrinkage area at the bottom in these areas, and also some corner areas. See the shrinkage areas with the bars inside. This is a problem which makes the casting rejected. It needs to be started. Why shrinkage is occurring? Insufficient feeding and the lesser riser volume. General reason: insufficient feeding, lesser riser volume, causes insufficient. Necking of the riser is also causing insufficient feeding. Let us see whether it is here or not. Overheating of the big bottom core also makes the metal remain hotter for a long time and gives rise to shrinkage areas. Too much of the inclusions in the molten alloy also can cause shrinkages. And giving you the general reasons. Section thickness is high means also shrinkage areas. Knife edges in die also can cause local shrinkages. All the above are the general causes for shrinkage problems to occur, shrinkage voids. Being made a kind of a YY analysis, the Japanese method, explain this and then go to shrinkage in the center boss area is what? And the problem was leakage in the pressure. Why? Insufficient feeding. Why insufficient feeding? All the three main risers are away from the pass. This is the leak area, but all the risers are isolated. And also, the feeding is not coming from the main risers because this section is hardly 4 mm. This is 50 mm. This is 115 mm. So, this solidifies first, make a neck. So, the effectiveness of the risers are not there. So, there is no feeding at all to this one. So, whenever you make a design, see that there is no necking of the risers. This is the main reason. We try to ask the and we can reduce the thickness there. Customer was kind enough to reduce it to some extent, which I will explain. Then the second way is overheating of the bottom floor. Why? The metal which is at 720 degree is fully falling on the top of this portion and then getting overheated, unlike the side gating. The whole metal is showering on the weak bottom core. It encourages the formation of shrinkages. How to make it? Try to cool. Then the third way is the casting thickness of the shrinkage area was 15 mm. It is also very high unnecessarily. We made a request to the customer and tried to make it from 10 to 10 mm. They agreed for it. Knife edges. In this corners, maybe knife edges. This section only 4 mm. So how the feed can come over here? So it solidifies first and this has got no use. The thickness only 4 mm. Here is 15 mm thickness was there. Plus made a 10 mm. See, the metal is getting, we are pouring through the control fire fan and coming over there. Everything is falling over it. And the whole core is getting heated up. And this portion remains very 400 mm. It's louder. I don't get you.
No, it's some disturbance was there. Now it's okay, sir. We can go ahead.
Then how to cool that? We want to try to cool it. First step is from 15 to 10 mm. Some shrinkage has come down, but not all. It's not acceptable. So then we try to cool it by putting copper pins like this all over the pins. We drilled and made with a lot of difficulties all the pins and blow air, compress air for cooling this. So that the coated temperature has come down from 400 to around 250 to 6 somewhere. Then we poured some castings and found that no shrinkages, no leakages, no problem at all. But the problem is different. But the side effects are very bad. That's what Japanese say. Whenever you find a solution and find the right thing, Also, if they to look at the side effects, the side effects may be good or bad. Here, the side effect was very bad. We are sending compressed air, and that air leaked through the copper chips. That's a pity of it. See, once you pour for some time, this is steel, or I mean, cassette. This is copper. There is a difference in expansion, and this causes gap after a month. And the air started leaking through the fins and causing problems. So we can't have a copper plug at the same time also this one. So we have to find some other solution. Although the castings are okay, but we can't work with this operating problems. One more operating problem was very noisy because you are spending minimum 6 mm diameter seamless steel pipes and putting very high quantity of compressed air. The whole shop was very noisy. Nobody likes it. Also, due to compressed air contains a lot of water and oil, it flows on the shop floor, makes it very, very housekeeping difficult. Workers did not like it at all. Also, the compressor got overloaded because of the constant application of air. Really, the cycle time is 5 minutes. For about 3 minutes, we have to apply compressed air and start. The solution given was not acceptable, although the casting quality was okay. So we have to find a new solution. A new method of cooling is to be found out. How to do it? The existing dia is about 150 dia. Inside about 120 mm diameter is hollow, totally hollow. It contains air. Air may be a bad conductor of heat, because we want to improve the conduction. So why not we try as a solid core? Because this doesn't look at no casting changes, but we are going to change the core. Instead of having a hollow portion, we want to go for a solid core. This is for the center core. This is the old, yeah. This is the newly designed solid core with the center core. This is the old design. There is no air cooling, no copper chills, and the solid bottom. The new core we made. And we poured about 100 batch quantity and many more and found there is no shrinkage problem at all. Totally okay. Everybody is happy, there's no air, no noise, no steam problems. Then the subsequent batches also okay. The problem solved. This is the final shape of this one. Yield is 58%. There is a increase. It was 48% was the earlier one. 10% was the increase in yield. The saving is enormous. 1.3 kg of metal, you don't have to pour at all. Monthly volume is 10,000 numbers, about 13 tons of castings, you don't have to buy at all. Tons of metal, you don't have to buy at all. That's a very huge cycle. At that time, it was about 40,000-45,000 rupees per ton. You don't have to invest that money on that one. No bandsawing is required. In the earlier one, the side races have got to be cut by sawing and then to be filed, finished. That work is not there. And also, the top 3 races were cut by one single cut by a rotary saw. One cutting, there is no bandsawing at all. Pour and cut and send it. So there was a lot of. Then, if anything cut by rotary sawing does not require finishing or grinding operations to make it even. So the casting, pouring, and one cut just by rotary saw, everything is ready for filing and dispatch. That is the saving. But the story at the end there. Lot of intangible benefits were there, no shrinkage cavities, no need for the compressed air, I saw all that. But the butt is always problem. But the die did not run well in operation. Why? Frequent shortage due to the jamming of the big bottom core, because Mortal metal enters into the core. The big problem. Production people was very unhappy. The solution was not accepted for patient because of the operating problem, obviously, which is how the metal enters. See, the metal is poured from the top on, the solid core, the metal comes down, which is about, this diameter is about 150, this diameter is only 152 or 153, and this is a core guidance, a die base, and the metal comes straight away here, this one, because the pouring height is very high. The 150 plus riser 170 the metal is flowing 1.5 kilograms of metal is flowing through this one. It gains a velocity of nearly 2 meters per second. And suddenly there is a gap of 0.4, the metal goes inside. So how to solve this problem? Because once in about 2-3 hours, every time you can't dismantle the core and then remove the aluminium there. The metal speed was calculated by a formula root of 2gh into 0.5 by gravity, 2.1 meters per second. So the gap is 0.4 per side. This gap, what I am saying is only 0.4 is required. And we thought, why not make it little less so that metal won't go. Again, we followed a method of YY analysis for the bottom work change. It's our practice. Metal enters into the core gate. The phenomenon. Why? The gap between the bore and core shank was 0.4. Then the gap is within 0.2, 0.1, metal doesn't enter. If it is 0.4, it enters. And we try to reduce the gap to 0.2 mm per side near the new core. But when we tried this, because of the heat of that core, the shank getting expands and the bottom core jams because of the expansion of the shank of the core. So 0.2 is too tight. So we need to have for 0.4 is a must. It is fixed now. We cannot go lower gaps. At least a 0.2 is required. If we do it, no metal, nothing is there. The core works with the molybdenum. Then we put some on the shank, some molybdenum sulfate for lubrication. It works for half a day or 1 day. The next day it changes. Molybdenum sulfate was put on the shank and it was working with the 0.2. But this you can't dismantle a big die for every day and then doing it. So it amounts to say the minimum of 0.4 is a must between the guide and the core shank. We can't skip that one. And how to make it? One solution came out. If the metal speed can be reduced or retarded, the metal won't go there. That is, shift the parting line away from the metal entry. You want to buy that one, we have to go for again a new core with a bigger shank diameter. The core diameter was increased to 152, 180 mm, the shank portion alone. This is the shank portion, old one. This is the new one. 180 the shank diameter. This is 154 diameter. The metal comes there with the metal and comes straight with a 2 meters per second speed and straight away finds a gap of 0.4 and goes on it. In this bigger gore with this bigger shank, the metal comes down straight away and then it finds no, the parting line is away. So if there is a 90-degree turn is given, the metal goes here and fills the gas. In this one, there is no metal entry at all in this core way. With the 0.4 gap, the die was working very well. This is the core way. This is the core guidance, and metal enters. Here, the metal is deflected because here a very small one. This is there is a 20 mm is there. Comes here, hit it, let the speed go down, and then this was very successful. So we were able to operate by 0.4. To keep the casting on the die, we put 4 pads like this, so that the casing stays on the die base so that we can remove it. By this modification, metal did not enter and the core did not jam. The casting on the die base, they got the die worked very well. This was a grand success. This is the end of this 30%. Coming to second. This is the end cover, a very small casting, but it has so many problems. This is one small aluminum casting, alloys 1124. Very small casting, 123 by 40 at 10 mm with 2 bars. But the casting yield is the full casting weight. This is a small casting and a very big riser on this rectangular portion. Riser, but yield is hardly about 30%. Short weight was 30 grams. Not only the yield problem, operating problem was very heavy operating. So the hell to operate. This is also strictly will be very difficult because this is a 25 mm thickness all over the area. Is hardly 10 mm. Holding it by hand and then sawing it by bandsawing is very difficult. It has also got 2 top coats. Very difficult to work. I will show you the die construction. This is a 2 impression die. Die base is a die half. This is a die half. These are 2 top coats. This is the 2 cavities sunk in the die. This is the view. This is the 2. This is the top core 1. This is top core 2. All to be levered for removing. The whole cavity is sunk into the die base. And it is a pouring system. We pour in this one casting and also pour in this one. There is, and the casting has ditches to be levered and removed, each weighing about 10 kilograms of each core. Every time operator. And also there is no ejection system. Made of, I say, Rakanpini and hydraulic, nothing was there. Only a solid one. Operator has got to lever the casting and then remove it. The hell of a job. There was no chance for no way for modification of the die. So I recommended the die to be scrapped and then there is no other way. It was accepted and a new die was made. This is the new die, simple die. This is one fixed die, very simple die. This is a moving die. This is occupied by a toggle. This is die base. One is fixed here. And it is also a runner catching point. So the casting will not move, go with the moving die. Very simple construction. This is also a 2 cavity die pouring from the top. A simple thin riser. Because I said, the earlier one, castings which are very thin need not have feeders as per camber. So this is the side feeder. If you want, we pour from this. A very simple work. The short weight was 198 grams as against 300 grams. Net weight is 120 grams. Yield went up to 60.6%. The die construction was simple, only 2 die casts. Cutting of the riser was very easy, unlike the other one. The end. Now let me go for the third case study. Manifold. It's something different. This is a very long, thin casting. Hardly the thickness is varying from 5 to 6 mm. Very, very long. This is about a meter long. And then the mm, this is about the mm. The back side of it is hollow and formed by Sanko. See, but the weight is 9.5 kg settled weight. This is one casting. I will show you the short present. See, you see everywhere there is risers because lot of leakages were everywhere. Here we pour metal, comes down, and by the time it goes to the end of 900 meter, all getting cooled. These risers raise up. See, the metal comes here and goes down and enter from the bottom and try to go. The bottom gating, the horrible design. Metal won't go through this one. It will fill up only after going to this one. I don't know how it was designed. And by the time the metal goes from here to here, you get lot of sharp rejections of cold sets and shrinkages. Two men were pouring the die, and casting also stuck with the die hob in which there is no rejection. It was difficult to remove the casting. See, casting removal, if it is stuck in the moving die hob, the big problem. I will show you the die design. This is the die like a PVC die. See, this is the fixed die. With the ejection, casting supposed to stuck here. This is a moving die, it moves. This is a tie bar. Nobody goes tie bars like this for static gravity. This is pulled by, this die hob is pulled by hydraulic cylinder. This is rolling on a beam. All that. And by this knee, you won't be able to touch up the die cavities for coating and all. You see, it looks like a PVC die. Horrible design. Anyway, die has been made. Now, I express my view, a strong opinion. This casting cannot be produced by static gravity at all. This casting is not meant for it. I recommended to go for a tilting gravity die casting. I guarantee you such will be other. It was agreed, a lot of loss, they made 2 dies, nearly 10,000 lakhs has been lost. Finally, there is no other option except to go for a tilting gravity die. I guaranteed 100% success. This is the redesign of the casting. Full shot. You pour from here, only hardly. You pour all the metal enters. You put up a pouring bowl over there. Just tilt it. Have a lot of air vents. So the metal comes from all the places right away from the mouth. This is the die. Same die was modified, removed all the races and fitted into the machine, and the whole machine was tilted and poured. It was the first shot success. And this is the shot. For some reasons, I am not able to give the full details. This is the only 4 or 5 races, no other race. And sand core is here. And the settling is like a cakewalk. You just cut it. The casting was still running well, being fitted day in and day out. This is the cut section after cutting the races. This is the end shot. Settled weight to and that doesn't change. The full shot weight in this is 4.5 only. Yield, the tilting grade method is 76%. Yield was 48%. Improvement was 76 minus 48, 28%. Quality was excellent and settling up here and success yes. End of the time. Any questions you can ask?
Sir, this is Yuvraj, sir. I have one question. See, we have a project for Ola. Okay, it is a frame and footrest, right? So the material is ALSI 10 mg, and their requirement is that yield strength should be minimum 210 megapascal MPa with elongation of 4 to 6%. And they want to make this casting with heat treatment if you're not getting the minimum of 210 MPa, sir. So we are doing it on pressure die casting method.
Oh,
So if you have any, yeah, they are open with any other alloys also.
oh.
Any
At present,
like structure.
At present, the process high pressure.
Yeah, sir. Yes, sir.
Yeah, high pressure castings cannot be heat treated. You said that you are heat treating it.
No. See, if you have, I'm not getting 210 minimum. So they are asking for any other process. It can be heat treated or it's just a suggestion they gave me. So
What is the
I
size
want
of the casting? Size of the casting?
size of the casting. 1 minute, sir.
மைட்டப் ஒன்று கொடுத்துருக்காங்கல்ல எல்லாம் ஸ்கேன் பண்ணி கொடுத்துருக்கேன் சார் ஒரிஜினல் மட்டும் ஃபைல் பண்ணிட்டு எடுத்தாங்க.
Sir, just 2 minutes, sir. I'm just giving the height, weight of the cast. Yeah. Sorry, sir. It will be around 1 to 2 kg, sir.
1 to 2 kg. Actually,
yes, sir.
If the shape is known, I can answer well. But you can even go, if the volumes are justified, you try to go for tilting gravity.
Okay.
Yeah, unless I see the casting or the drawing, so because selection of the process is very important. Either static or tilting or.
Oh, sure, sir. Sure. Maybe when I meet you personally, I can show you, sir. I can show you the drawings.
You can
I'll get
take my
it.
mail ID or even WhatsApp number from IAF, and
Yes,
then send me the photos. I reply to you, no problem. This
Sure,
is my
thank you,
number.
sir.
You can just write down.
Yeah, sir. Definitely. I'll do it.
Yeah, my number is 98-402-56816. 98
Yes, sir.
402-56816. Even you can send it by WhatsApp now. I can answer you.
Sure,
Just
sir.
a
I'll do
photograph.
that, sir. Yeah.
Any other
Thank you, sir.
question? Thank you.
Sir, I'm Bapat. I have one question.
Yes, sir.
In this process, you did not alter any pouring temperature, right? Or any specific pouring temperature you preferred?
For gravity, in India, they follow 700 to 720. For alloys like LM4, LM25, which are the most commonly used alloys. In Korea, for this casting like LM25 and all, they used to, you may believe it, 695 degrees centigrade plus minus 5 degrees. I have seen it in Korean foundries. But when I check the floor, actually, it is not so. 695 plus minus 2 degrees. Something they put a chart and then there is a continuous recording of the metal temperature. They get a very good casting. And they follow the tilting gravity casting. But unlike in India, the degassing time is 45 minutes. You may not agree or believe in it. Here we do it only for 10 or 15 minutes. I asked, why do you so much of 45 minutes of, they want to take out the micro inclusions with the fluxes and then keep on this one, and the transfer rails are preheated. By that one, we are able to avoid them. The metal is like silver. So metal quality itself will give you lesser problems. Many problems can be solved by metal itself. By keeping a very nice one.
Like this is important input. I think I have not seen many foundries following this.
Yeah, they go to, actually they buy material, but they don't keep it properly. So you buy rice, but you don't clean it up, You keep all the markings.
Yes.
The rice is good, the cash will be good. Like that, metal is the basic one. Now Japan, wherever they went, they treat the metal like silver.
Thanks.
Metal control also is very good. Here they give, what is the metal temperature here? They will say 720 or to 740. It's such a wide range is horrible.
And also, yeah, and also I felt the mold filling time is different in foundries where I have gone. So, do you have any comments on that?
Yes. Actually, molding filling, normally, as they say in the laboratory and all, we cannot do it in the shop floor. So I have a thumb rule on this ones. You keep the molten metal filling time 12 seconds. Plus minus 2 seconds. Plus minus. Not low or not this ones. You adjust to this one, the gate entry 2 seconds. Because if you keep very long filling time like 20 seconds, 30 seconds, metal in the ladle will get cold. You agree with me? So then
yes,
the
100%.
is getting cold in the ladle, operator has got to hold it, or the autoladle has got to remain hotter and become all that one. So in my practical experience, I try to keep the filling time for any casting possibly within 10 to 12 seconds. And then I will adjust the pouring gauge. But the pouring is to be done very carefully, because pouring is one of the very big problem in the casting design, apart from your feeding. So the metal must enter, as per Professor Campbell, with a 0.55 meter per second. Practically, it is not possible. I went up to 1 meter per second. So that there is no cold stress, metal won't get cold. So you can go up to 1 meter per second, the metal gate entry velocity. To avoid the air going into one, you can follow the ratio I shown, 1:4:2, the cross-sectional area of the various components of your running system. I can guarantee you there is no air will go inside it. That will give you a free fun, because air is a big problem. Then how to find out whether air is going inside your casting? You can't do X-rays and so on, What you should do as soon as you pour a new casting, say take 1 or 2 samples on the new die, get it 2 times short blasted, not sandblast. Short blast 2 times heavily, and look at that surface of the short blasted casting. You will find small round holes. If that is there, something wrong with your gating. It's a practical way of assessing the casting. If there is no holes, leave it. Your gating is working. That is the first one to be done as soon as you make the casting practically first sample. And look for the whether the gating is verified, whether there's any air is going with your metal. You pour metal, not only metal, you also send the air in it.
Yeah, that is right. One problem I could solve in that way. What I did is they were pouring from the floor. I just asked them to give some platform. so that the height was the labors, they were able to pour it fast. That was one thing I found. I think now I can correlate what you said to that.
See, whenever you pour metal by hand ladles, I'm not talking about artla also, you must keep that nose of the ladle very close to the pouring basin.
Okay.
You should not lift it up and then pour if you want to pour fast this one. It is the biggest mistake many small foundries do. By lifting the ladle above the pouring basin, about 100 mm, you send the air, you form oxides and hydrogen pickup. It is a big, many small foundries do it. So you keep the ladle as close as possible, ladle nose, and pour very nicely.
Okay, thanks.
Thank you. Thank you.
Any other questions? Any other questions, please? Okay, if there is no further questions,
Hello,
I would like to
I
propose.
was just asking only one question, that is, sir mentioned degassing as 45 minutes, right?
Yeah.
Oh, okay. Thanks.
Any other questions, please? Okay, if there is no further questions, I'd like to propose a word of thanks. I'm Prabhakaran from Chennai chapter. I'd like to thank all the audience who made this event a successful one. And thank you all for taking your time and joining this wonderful session presented by Mr. Thirugnanam sir, who shared his invaluable experience throughout his life, throughout his career, which is wonderful and thought-provoking one. Thank you, Thirugnanam sir, for making this event a wonderful one. And we would like to hear more and more such presentations from you. We will try to keep more and more sessions with you, sir. Thank you very much.
Thank you.
Thank you, IF Chennai chapter, Southern region, and Non-Ferrous committee for making this event today. And thank you, one and all, who joined for this session. Thank you all.
Sir, I had a small request. Any participant can give their feedback, and also if they can give the topics, what they would like to hear from next speakers and everything. It will be good to get some feedback from you on some different topics which you are also equally interested. Okay. Yeah. Sir, thank you very much. Thanks for attending and thanks for giving a wonderful lecture. Though I am not coming from non-ferrous field, I was able to see the depth of knowledge you were sharing, and with a lot of efforts, a presentation what you have prepared. It was really great. Thank you very much. On behalf of IIF and non-ferrous committee, national committee members, I will thank you. Thank you very much, sir.
Thank you very much, sir.
Thank you.
Yeah. Sir, Mr. Hiren has raised his hand.
Yeah. He can.
Yeah, so first of all, thank you from Vadodara chapter. I belongs to Vadodara chapter. Last week I met to Mr. Suru, and this is the great startup. So I request Mr. Suru, if you can arrange some webinars on the copper-based casting, so that will be also beneficial to us, as he asked the topics intended for the next few webinars. So
Yeah, sure,
please,
sir.
yeah.
Yeah.
Thank you, sir. Thank you.
Okay. Thank you. Thank you, sir. See you again.
Okay. Thank you.
Thank you.
Thank you. Thank you all.